Zinc is a chemical element. It has the symbol Zn and atomic number 30. It is a slightly brittle metal at room temperature and has a shiny blue whitish appearance when surface oxidation is removed. Zinc is the 24th most abundant element in Earth's crust, with an average concentration of 70 grams per tonne. The element is normally found in association with other base metals in the form of ores. The majority of zinc is used in protecting steel through galvanisation, helping prevent corrosion. It is also essential in batteries, alloys like brass, and a wide range of everyday products and chemical applications that support modern life. Zinc is used in many different ways, and this diversity creates multiple recycling and recovery pathways. Some zinc products, like roofing and castings, can be directly remelted into new alloys with a very low carbon footprint. When zinc is used to galvanise steel, it follows a different route. It can be recovered during steel recycling, then returned to zinc smelters after processing. Some uses, however, are not recyclable. Zinc in fertilisers support plant growth and human nutrition, but once in the soil, it cannot be recovered easily. Nevertheless, food production is considered a necessary offset. Zinc begins its journey deep within the earth, where it naturally occurs in rocks alongside metals like lead, silver, copper and iron. When concentrations are high enough, these materials are mined as ore. Once extracted, the ore is processed in concentrators. Here it is crushed and separated into zinc, lead and copper-rich concentrates. Zinc concentrate typically contains more than 50% zinc. Around 95% of global zinc production uses variations of the roast-leach electrowinning process, known as RLE. This is an electricity-intensive route which makes primary zinc production largely Scope 2 emissions dominated. The result is special high-grade zinc with purity of 99.995%. It is cast into ingots or jumbos or directly formed into alloys used in galvanizing and die casting applications worldwide. Around 95% of the world's zinc is produced using the roast-leach electrowinning process. This method uses heat, chemistry, and electricity to extract pure zinc, making it an energy-intensive process. Although often labelled as primary, special high-grade zinc already contains recycled material. On average, this accounts for around 15%, typically ranging from 0 to 25%. Unlike the perceived everyday process of metal recycling, this material does not come from metallic zinc scrap. Instead, it comes from zinc-rich industrial residues. Most importantly, crude zinc oxide, or CZO, where zinc concentrations are well above 50%. The largest source of crude zinc oxide comes from steel recycling. When galvanized steel is recycled in electric arc furnaces, zinc separates from the steel during melting. The zinc is carried into electric arc furnace dust, commonly known as EAF dust. This material contains zinc, but usually at concentrations too low for direct use in zinc smelters. To make the material suitable for zinc production, An additional enrichment step is required to increase the zinc concentration. Electric arc furnace dust, or EAF dust, is classified as hazardous waste and typically contains only 15 to 35% zinc. At these concentrations, the material is below the threshold required for direct use in zinc refineries. The most widely used enrichment technology is the Waltz kiln, which increases zinc concentration to around 55 to 60%. These enrichment processes rely on carbon-based reductants such as coal or coke. As a result, they are heavily Scope 1 dominated and can generate a carbon footprint greater than zinc mining and beneficiation. The enriched product is known as Waltz oxide, more generally referred to as crude zinc oxide. Future steelmaking routes, including hydrogen-based direct reduction combined with electric arc furnaces, are expected to increase the volume of EAF dust. This could lead to two very different outcomes. Either more zinc is recovered and recycled into special high-grade zinc, or more hazardous waste is sent to landfill. A key uncertainty is zinc concentration. If future dusts contain less than about 15% zinc, today's Waltz-based recycling models may no longer be viable. This makes innovation and the scale-up of new recycling technologies essential. About 60% of all zinc is used to protect steel from corrosion. As a result, steel recycling has become the main recycling route for zinc. Research is now focused on replacing coal with hydrogen, applying carbon capture technologies, and developing fundamentally new recycling processes. These solutions are advancing, but are not yet available at full industrial scale. Until viable alternatives are ready, the only option besides enrichment is landfilling hazardous waste, consequently losing valuable zinc and other metals that could otherwise be recovered and reused. Two different carbon footprints are used in reporting: the product carbon footprint for special high-grade zinc, and the corporate or site-specific footprint for zinc smelters or producers operating multiple facilities. The International Zinc Association Carbon Footprint Guidance defines a harmonised methodology for calculating and reporting the product carbon footprint of special high-grade zinc. Covering Scope 1, Scope 2 and selected upstream Scope 3 emissions, the framework aligns with international standards, including the GHG Protocol and ISO methodologies, while avoiding double counting between steel recycling and zinc production. In this framework, emissions from EAF dust enrichment are allocated to steel recycling, because this process converts hazardous waste into a usable raw material for zinc production. This methodology is recognised by the London Metal Exchange and supports LME passport reporting and future sustainability premium pricing concepts. Product carbon footprints allow zinc users to compare materials from different suppliers and support their own sustainability and reporting obligations. Corporate and site-specific footprints are used to assess financial and transition risks at the company or asset level, including the full Scope 3 emissions spectrum. Both perspectives are valid, but they answer different questions. For product carbon footprints, emissions from the Wälzing process are allocated to steel production. For corporate or site-specific carbon footprints, those same emissions are included at facilities that operate Wälz kilns. The emissions are the same, but their allocation depends on the reporting perspective being used. The imperial smelting process, or ISP, is a pyrometallurgical route that produces zinc and lead simultaneously from a wide range of primary and secondary materials. The ISP process typically has a higher product carbon footprint based on emissions intensity. However, both RLE and ISP processes have their own place in the zinc industry. The imperial smelting process simultaneously recovers zinc and lead, and with the lead also recovers silver, gold and copper. This helps avoid landfilling of hazardous waste while recovering valuable resources. From a narrow carbon footprint perspective, zinc produced through imperial smelting and roast leach electrowinning routes can be compared. But from a broader sustainability perspective, carbon footprint alone does not tell the full story. Circularity, zero waste performance, and the recovery of critical metals from both primary and secondary raw materials must also be considered when evaluating the overall sustainability of zinc production routes.